One of the strongest points or aspects of GNU poke is that it is extensible. And basically that means that even though GNU poke comes with descriptions, already written descriptions for many formats, or binary data formats, or file formats, or protocols descriptions, it's always possible to actually extend it yourself. And it's not only possible, but that's something that you will probably want to do in any case, because even if poke comes with a pre-written description for some format that you want to use, it's very likely that by the very nature of what this program is used for, it's very likely that you will want to either extend the description or to change it or modify it. So one of the best ways to learn how to do something is to look at particular existing examples. And if the examples used for pedagogic purposes are not just toys, but real things, and it's even better. So this is the first video in a planned series where basically we are going to show you how to write pickles, which is, the data format descriptions that we use in poke, using the poke domain-specific language, for by showing existing pickles which were written for real world purposes. So we will start with a little pickle which is used to access GCOV data files. I wrote this pickle last weekend because of some need I had, and it's a small one, but it has it exemplifies well some fun and interesting aspects of writing pickles and the poke programming language. So that's why I chose this particular one. So okay, let's get started quickly, because my videos, they have the tendency to be endless. So let's get at the point. So what is GCOV? GCOV is acronym for GNU coverage, and it is a functionality that is provided by the GNU toolchain, but the GCC compiler in particular, in order to provide coverage reports for programs. What is a coverage report? Okay, let's consider I have here a little toy program, C program, which is called foo, that has a function foo. It has a main function main, and basically in the main function it has a for loop that iterates over argc. Argc is an argument that the program gets from the kernel, from the operating system, which is basically the number of command line arguments, including the name of the program gets. It's just iterating on it, and it's calling foo in the loop. And then it's looking at what foo returns accumulated, and then it's either returning 0 or 1 to the operating system. Very, very simple. Very simple, stupid program. Okay, so if we compile this program and we pass the ---- coverage option to GCC, then what we have is we have the compiled program executable, which is this foo, and GCC also generated a file which is called foo GCNO, and GCNO means GCOV nodes file. So this is a GCOV nodes file that is generated by the compiler, that describes, we will see later what this contains exactly, describes some aspects of the compiled program foo, oriented to actually do the coverage. Then, since we specified ---- coverage when we compiled foo, the executable foo contains instrumentalization code, meaning that GCC obviously generated the executable instructions corresponding to the C program that we were compiling, but also since we invoked it with coverage, it also generated some additional code in this executable that it makes basically calls to some runtime library functions that are calculating and accumulating statistics when you execute the program, and they write them out in a file. And well, if we execute the program foo, okay, we executed it once, right, with no arguments. It generated a foo GCDA file, which is the data file. And if we run, well, basically this contains the statistics. So we run foo once, no arguments. Let's run it again with 3 arguments. Now this updates the data file, right? And so basically this was created by as a side effect of running the program itself. So both the data file, as you can see here, and the nodes file, they are both binary files. They are both binary files. But GCC also provides a utility which is called GCOV, that if you execute it on the data file, it creates a report. And this is a report that people can actually read. So this report says that there are 2 runs because we executed the program foo twice. And then we have the accumulated statistics of coverage per line here in the program. So for example, we executed the body of the for loop 5 times. So remember, we invoked foo once, that counts for 1 execution of the body with no arguments, and then we invoked it again in the second run with 3 arguments, plus the name of the program 4, plus the previous run 1 is 5. And obviously the function body is executed 5 times, right? Okay, so basically the GCOV utility, which is a C program which is provided by GCC itself, it went from using the information from this nodes file and also from the data file, we get a very nice printed report. All right. Now, what I needed to do, and I used poke for, was to actually mess or look at those files, the data file and the nodes file, and those are binary files. So poke was, the natural choice for me. But then I needed to teach poke about how to access and to deal with this binary data. So the first step for me was to actually look at how that information gets encoded, what information gets encoded in those files and how. And in this particular case, this is an internal format defined by GCC. Even though GCOV is also used for profile guide optimization, which is implemented by more than one toolchain, because LLVM also implements it, and that means that probably some interoperability is going to be necessary. In principle, this is an internal format because it is GCC that generates those files, either GCC directly, like in the case of the nodes file, or indirectly via the instrumentalized code in the generated executable. And also it is GCC, in this case the GCOV utility, that consumes the same information, the same format. So the logical place where to go to look for this particular format was in the GCC source code. So I did, and then I found several files here and there, so I had to go and look and understand the implementation of GCOV a little bit, and I found a header file here that has a more or less accurate and more or less up-to-date description of the encoding of the contents of those files. And so then my next step was to somehow transform this description here plus the C code, the corresponding C code, macros, masks, and everything into some pickle that I could use with poke. And the result was a pickle called GCOV.pk. This is what I wrote over the weekend. So this pickle is able to understand the contents of both kind of files, the data file and the node files, and overall is 436 lines long, which is not that long. Okay? So basically, the first thing, so when I looked at the GCC source code, the internal source code, and that header file, I learned that both data files and node files, they have a very similar structure. Basically, they contain records, something called GCOV records. And some of the GCOV records are common. They can appear in both data files and node files. Some of them are that specific to data files, some of them are specific to nodes files. But in any case, what I did was I started with the most basic encoding of the file. So then I learned that in the most basic sense, in the most basic level, in a GCOV file, be it data or nodes, everything is encoded using three different, some sort of basic types or basic data structures, which is, the first one is signed 32-bit integers. A GCOV signed 32-bit integer is stored as a signed 32-bit number, but it is encoded in whatever NDNS, well, here I wrote used by the machine generating the file. So this basically means whatever NDNS used by the target of the compiler generates the GCOV files. So in this case, this GCC I used is a GCC for target to an x86 machine. So basically, both the nodes file generated by the compiler itself and the data file generated indirectly via the instrumentalization code both use little endian. Okay, so those are the 32-bit signed integers in GCOV files. So basically, for that we can just use the poke int32 type because it behaves exactly like that, right? So there is no mystery here. However, GCOV files also can contain 64-bit integers, and in the case of the 64-bit integers, the story changes a little bit because it's a little peculiar encoding. So we can read in the GCC source code 64-bit. We can read this. We can read 64-bit numbers are stored as two 32-bit numbers. So it refers to the 32-bit numbers as in GCOV. The low part first, right? So this is how can we encode this in poke, right? So again, 64-bit numbers are stored as two 32-bit numbers, the low part first. So basically, it is two things, like in this case, two 32-bit numbers, so it should be a struct. So GCOV int64 is a struct, which first, it has an 32-bit integer, right, which is the low part, and then we have another 32-bit integer, which is the high part of the 64-bit value. So note something interesting. The low part always comes first, meaning that it is stored lower in the IO space, and then the high part always follows, regardless of the NDNS used. It doesn't matter what the NDNS used. Low comes first, then the high comes next. But each of those components, so the low part and the high part, by themselves separately, they are impacted by NDNS because they are like the 32-bit numbers that we saw before. So basically, this is how you do it in poke. You just have a struct in poke. What you poke is what you get. You have a low part followed by a high part. Those are poke integer type, so they are impacted by NDNS. And for convenience, we have a pretty printer. And how do we pretty print things in poke? Well, we define a print method, a method called _print, that in this case, following the convention that we use for pretty printed values in poke, when we write pickles and we use pretty printers, we have the convention that the pretty printed value is always delimited by dash less than and bigger than, following a little bit in the Lisp tradition, right? And basically it prints in 3064, and we bit concatenate. This is the bit concatenation operator in poke. It bit concatenates the high part with the low part. So the bit concatenation operator in poke, which is unusual, but you know, I mean, that's why poke is a domain-specific language, and we like it that way. Basically, the high part is a signed 32-bit integer, and the low part is an unsigned 32-bit integer. This means that the type of the result of the operation is a signed 64-bit integer with the expected value. So actually, we can look at it. I run poke, log GCOV, log GCOV, and then This is a info type GCOV int64. It has the low part and the high part, right? And the print pretty printer. So basically this is how it works. Okay, let me set. So this is, you know, this is the way it works. So if I only specify the high, well, it is only the high and so on. This is what pretty printing on. If we set pretty print off, then we get the full thing, the whole thing, right? Okay, so this is for GCOV integer 64 numbers. Not something, I mean, this is not a usual way of encoding 64-bit integers, but in POC we had enough artifacts and abstractions to do it in a relatively, well, not relatively, in a very straightforward way. Okay, let's go back to the spec. Well, spec, yeah, well. Now, then there is the strings, the strings. The strings are actually, okay, this comment in GCC needs some love, but okay. Basically, for strings, it says the number of bytes is stored. The number of bytes is stored as an integer, I will add, you know, as a 32-bit integer, followed by the string itself. The string itself is like a C string, which is a null terminated string. But then it says zero length and null strings are simply stored as a length of 0. So they have no training null, right? So basically, translated into POC terms, we come with something like this. So basically, okay, this from what I read in the comment in the GCC source code plus what I saw in this implementation, basically I reformulated it in this new formula, which I think is more clear, which is in GCOV, character strings are stored as a length first encoded in a 32 bits number. Okay, here we go. There is a length encoded at a 32 bits number, integer, signed integer, which denotes the length of the string, of this whole overall GCOV string, counting the training null character. So in case we had foo, for example, as a GCOV string, we will have a 4 encoded at an int32, which is foo 3 characters plus the null character, training null character is 4, plus followed by a string, which is a POC value, a POC field with a POC value, which is a string, null terminated string with containing foo, right? But only if the length is bigger than 0, right? So a 0 length string will be encoded as a single 0 encoded as an integer 32. And that's how we encode this in POC. This is how we translate this specification, this spec, into a POC type in this case. So first we have the length, we always have a length, and only if the length is bigger than 0, we have a data field. So this is an optional field, what we call in POC an optional field, which is a field in a struct whose presence depends on some factor, and in this case some condition. In this case the condition is a precondition. We also support conditional fields, which basically is this field only exists if length is bigger than 0. And when it exists, we have here a constraint expression for this field, which is when it exists, its length here is in POC for a string. If you have, for example, this is the attribute, it is 3 for, and size is okay, 20 bits, 4 bytes, right? So length is the length of the string, not counting the null character, the null character. So basically, the constraint here is that the length of this string should be this length minus 1, because length here, it includes the null character, right? So this is how we do it in POC. Now we have, for convenience, we have here a getString method that basically, if length is bigger than 0, then it just gives us the string here. But if length is 0, there is no string field, no string stored, but it just makes 1 and gives it to us. And a nice pretty printer. Again, we can play with it. So if we construct a new GCOV string, it's an empty string. But an empty string, again, pretty print no. An empty string, look, is just a length. There is no data field. But if we construct a new string and we say that the length is 3, okay, then we have to specify a data. In this case, why? Because otherwise there is a constraint violation exception because the constraint fails. What constraint fails? This one. So if we have length 3 data xx, 3 is xx plus the null character. If we say foo, we get another constraint violation exception because the constraint is not. We will need either to put length 4 or to change the string. Okay, and in this case that exists. And if we pretty print again, okay, so this is the length is 4, then we have the nice printed value here, string 4. And also we have a method get a string, which is basically giving us the string that is useful, if we want to actually access it, index it, or whatever, right? Okay, so basically that was the first step to write the pickle, right? So the spec says 32 bits integers, 64-bit integers, and character strings, right? And GCOV strings. So the 3 types that we those are all the types that POC knows about that start with GCOV. So basically this was, for the integer 32, we just use the native int32 POC type, so no need for a GCOV int32. For 64 bits we use GCOV int64, and for strings we use GCOV string there. Okay, cool. Okay, so let's go on. So this is basically the most basic encoding, right, of the file. Let's go to what about the less basic encoding, which is the files themselves. Okay, we have seen two different kinds of files, right? We have seen GCNO files, which is the nodes files that the compiler generates, and we have seen the GCDA files, which is the files that the instrumentalized program generates when it runs, or updates when it runs, right? And this is what they are. Well, the spec is also specifying this, but okay. So let's say, for example, the data file, right? The data file, remember, this is the GCDA file that is generated by the instrumentalized program. We are starting with the data file because it is simpler than the nodes file. But as you can see here, both files are more or less the same thing. So I said at the beginning of the video that both files contains a set of records. So those are arrays here. So, but let's focus first on the data file to not get lost. Okay. So the first thing that we have in a data file, and actually also in a nodes file, is a magic number. So magic numbers are common idiom used in binary files, which is that it's some sort of magic sequence of bytes at the beginning of the file that identify the contents of the file, and sometimes and often also provides some details on the morphology of those contents. For example, the DNS. So basically, in a data file, we have a GCOV magic. We will now see what is a GCOV magic. A field called magic, which is the magic number, and we are using here this POC idiom, which is equal, which basically means that this is a short economic way of expressing both a constraint expression and an initialization value. So basically this says that magic, it should be GCOV data magic, that we will see now how it is defined. And also we are saying that when we construct, when the user wants to construct a new GCOV data file, it should be initialized to the same value, GCOV data magic. All right, okay. And then there is a version, a stamp, and checksum. Okay, but let's stop at the magic for the moment. So GCOV is a small format, but it is tricky enough. That's why I chosen it for making this video, because it's an interesting one, a fun format. So what is a GCOV magic? So basically it's this. This is what I came with in the pickle. Okay, so GCOV actually uses 3, it's not 2. It's not just data nodes. There is also a no file, we will explain it later, called file name, but let's forget it for now. So it uses different kind of files or elements in a stream. So each file characterized by the magic numbers is characterized by the magic numbers below. So what is a GCOV magic number? A GCOV magic number is an 32 bits integer, right? That follows certain conventions and structs, right? But they are 32 bits integers. They are. So if we open foo.gcda and we dump the bytes, we see that the int32, well, actually, let's set the endianness to little, because what we explained before. So the int32 at 0 bytes is the magic number, and here we see in the ASCII dump that each byte of the magic number corresponds to an ASCII character, which is ADCG, but in Little Endian it's GCDA for GCOV data file, right? Okay, so basically it is stored as a 32 bits integer following whatever endian started by the compiler, but we are using here what in POC is called an integral struct. An integral struct is like a normal struct, but it actually specified here that this struct should be stored exactly like an integral type, meaning that when POC, usually if this will not be here, what you POC is what you get. I mean, POC will always, independently of endianness, always store and read C1 followed by C2 followed by C3 followed by C4, which are bytes right here. But since it is an integral struct, then if the endianness is little endian, it will store first 3 4 3 then 3 then 2 then 1. If it is big endian, it will store it 1 2 3 4, right? So we are using an integral struct composed by 4 fields, C1, C2, C3, C4, which are all the bytes, and we have here a pretty printer, following again the convention for pretty printers, that basically it is printing the 4 characters. And then we are, well, if we construct a GCOV magic, okay, well, this is pretty printed, and this is with no pretty printing. All the 4 bytes is initialized to 0, right, as expected. So then we define 3 variables, because the POC variables, and we are using constructors for constructing the magics. And we are using here the notation for characters. So then the magic number for GCOV data files is the magic number built from the constituents GCDA, GCNO for nodes, GCFN for the file name no file, we will see at the end of the video. And note that we don't have to specify here explicit versions for little or big endian, because since this is an internal struct, POC will do the right thing depending on the endianness which is configured here. Actually, we can see that. Why not? Let's create an empty IO space, because I don't want to vandalize this the GCOV file, and let's say GCOV magic C1 equals A, C2 equals B, C3 equals C, and C4 equals D, right? A, B, C, D, and the endian at the moment is little. So if we say GCOV magic at 0 bytes equals that, then it's stored in little endian. If we change the endian to big, and we stored at 10 bytes and 0x10 bytes the same thing, then we see that it's reversed, right? So this is nice because it makes life easier, and also it allows us to define those variables in a very readable way in the pickle, right? I mean, this is very easy to understand. Okay, so this is the magic. So for data files, the magic should be GCOV data magic, and for nodes file, the magic should be GCOV node magic. It's as simple as that. All right. Then in both files, both in nodes and in data, then a version follows. What is this version thing? Okay, this version thing is, well, a version, and this is versioning the contents of the file. So remember that this is sort of an internal format. So in the spec, it says that you should not expect backward compatibility, but it says we are versioning it. So this versioning can be used by consumers of those files to at least notice if in advance if they are gonna be able to understand the contents or not, at least in theory. Okay, so there is something called a GCOV version. What is a GCOV version? Okay, in both files, in both nodes and data. Okay, so let's take a look. GCOV version. So then I went to the GCC source code again, and I determined that it says that recent GCOV versions, so the current version in schema in GCC, this is git GCC, this is GCC 14 or 13, are stored as surprise 32-bit integers. As you can see, this basic encoding we saw before is actually real. I mean, everything is encoded in terms of 32-bit integers or 64-bit integer or strings, whose contents determine the value of 4 ASCII characters. So again, we are using an integral struct and with 4 constituents, which are the bytes. And in this case, the first 2 characters encoded in this integer is the major number, and the major version number is 2 ASCII characters, right? Then there is a third one, which is the minor, and then there is a fourth one, which is called the status. And so let's start. It says, the spec says, the first character in the major number, which has 2 characters, but the first one starts with a big A, uppercase A. So this versioning schema doesn't collide with a previous used one. Apparently, the versioning schema was different before. I have not looked at that because I don't care, because I needed to work with the latest GCC. But apparently, in this versioning schema, this character should be uppercase A or bigger. So basically, that's why we use a constant expression here, right? And we use the initial value for this, for when you construct new GCOV versions, is uppercase A, which is a reasonable default. Then the second character is the second major version, which there are no restrictions in it that they could see, so there has no constant expression, but the default value is a 0 character, ASCII character, which to me it looks like a reasonable default. The same for the minor, and then it follows the status. So from what I can see in the header file in GCC plus the source code, I noticed that it can be little e for experimental, little p for pre-release, little r for release, and I have seen that some GCC versions they generate star and also the empty character, the blank character, the white space character. So basically I added this constant expression here using the in operator in array, poke operator, which is handy for this sort of purposes, and as a reasonable default I used experimental because why not, and a suitable pretty printer. So again, GCOV version, if we just construct one, it's A00A, right? Okay, by the way, let's close this, and now we are back to the data file. Yes, okay, so this is the version, right? Then in both files there is a stamp and a checksum. So basically the stamp is some sort of number that the GCC sources say that it doesn't have to be a timestamp, even though if in practice it's likely it is, but it doesn't have to. It doesn't have to be a timestamp. But it should change often enough. So if you run several times, you would generate several times the file to distinguish those files, but not often enough. I mean, okay, it's used to determine if the file should be updated or not, you know, stuff like that. And then you have a checksum that I don't know exactly how it is calculated because it's not explicitly said. I could go to and look, but I actually don't care that much. I think the checksum is used to actually make sure that the data file corresponds to the GCOV, to the nodes file. So I don't think this is a checksum of the contents of this file. I think this checksum is to compare, but I'm not sure about that. But actually we can now take a look. Then in the case of the nodes file, there is a GCOV string with the current working directory. We have seen how the strings are encoded, and then a flag called support and executed blocks that I don't know exactly what it's used for, but it's just an integer. And then in both cases we have an array of records, right? Okay, so this is we have seen the most basic encoding. We provided definition for GCOV in 32, in 64, and GCOV string. Then we saw some intermediate encodings here for the magic, the version, and then the overall structs. Okay, so now we have here the data file open, right? So let's map data. So GCOV data file at 0 bytes. Okay, so an endian little. It failed in the magic number, and we know, so it must be the endianness, right? And let's open the nodes file, and then var nodes GCOV nodes file at 0 bytes, right? So that the pager is activated. Okay, so we have data. This is the data file. So it starts with the magic number, expected one, the version, B40, and then white space, a stamp, and a checksum, right? And then the records that we will see later. And then we also have the nodes with a stamp, a checksum, right? And magic, you know, and version, right? Okay, I don't want to divert the video, but now I am wondering, I can't avoid it. I said the stamp, we don't know exactly what it is, right? And it's not specified. It should be changed often enough and blah blah. But now I'm curious, what is this stamp, right? How could we figure it out? Well, could it be a timestamp? It could be. So in POC, we have a pickle for some time stuff, and we have time specs, and we have a POSIX structs here. So could it be a time 32 POSIX stuff? Okay, let's find out. Load time. So let's say, for example, data stamp, right? This is it. So it has a size. It is mapped, because this is we just mapped it, right? Sorry, data is mapped. So data stamp, it must have an offset. No, actually, the offset, it is the second, right? So it is, yeah, okay. Actually, wait a second. Info type, GCOV data file. So it is the third one, right? And the offset, so it is the third one. So the offset is 8 bytes, right? Which makes sense because this is 1, this is 1, this is no, it is the third one. So it is, yeah, it is 8 bytes, yeah, okay, yeah. So so is this a stamp at time? Well, let's find out. So at time, then POSIX time 32 at 8 bytes. Oh well, yeah, you see, it is. It is the 29th of May 2024. No, it's not, because we are in 2023. But okay, well, okay, whatever. Anyway, let's go back to the track, to GCOV. So yeah, so let's see the nodes. Then we have a GCOV string. Remember that it had this a little weird encoding, but now we have it pretty printed, which is nice. This flag support unexecuted blocks, which stands to be 1, and then we have a list of records. And for the data, we have similar header fields or first fields, and then we have a sequence of records. Okay, so let's take a look at the records themselves, right? So basically, in both files definition, in both type definition for both nodes and data, we are defining the records as a field, and the type of the field is an unbounded array. So in POC, when you map an unbounded array of anything, basically the rule is the following: POC is gonna map an array containing as many things, in this case GCOV records, as it finds in the IO space at the given offset, in a way that they are well formed. And what it means for them to be well formed, for those things? Well, in a way that there are no constraint expression that fails when it actually maps, in this case, GCOV records, or until it finds an end of file condition. It runs out, at the end of the file. So basically, let's take a look what a GCOV record is. So GCOV records are sort of generic containers, in a sense that each GCOV record is a tagged struct, in the sense that first you have a tag that identifies the payload stored in the record. Then you have a length. This length basically somehow contains the size of the variable part of the record, which is what the variable part is what depends on the value of the tag, right? And then after that we have a POC union containing the data or the payload. Look, this is the union. This is the field is called data. The union is called data. And then what is in data? It depends. Depends on what? On the tag. Depends on the tag, and then okay, we will see some stuff, but mainly on the tag, right? So if the tag is tag function, it has something. It has one GCOV function. If it has, if the tag is GCOV tag args, it has a struct like this, and so on. So so then we have each record has the tag, the length of the variable part, and a variable part. One record after the other. Okay, so let's start with the tags, because this gets a little bit tricky. Let's do it quickly. So what is a GCOV tag? A record tag. So a record tag, it has its surprise again, and a 64-bit signed integer. And this signed integer is composed by 4 components, 4 bytes, the 4 constituent bytes, which define levels. And don't worry if this is not clear right now, but as soon as we take a look to the currently defined tags, it will become clear. So basically, each GCOV tag is an integer composed by 4 bytes. So the 4 bytes are in order. I call them level 1, level 2, level 3, level 4, L1, L2, L3, L4, right? Those levels, they define a hierarchy, right? And when a level is used in a tag, the value is not 0. When a level is not used, the corresponding byte is 0, right? And if the corresponding byte is used, so it's not 0, the value should be odd. And the value must be odd. It should be odd because GCC uses this fact in order to speed certain calculations by calculating masks, like subtracting 1, then you have an F, then using an XOR, and so on. So the reason why this rule that if any of the bytes in a tag it's not 0, it should be odd, the value in it, stored in it. It's just because of implementation convenient in the C implementation. So, okay, but in any case, so we have that this is stored as an integer, so we are using an integral struct again. We have that each byte, it defines some sort of level from L1 to L4. That's what we are having for fields here, and we have rules. So the rules, we are encoding them as constant expressions. So the rule that the byte should either be 0, but if it is not 0, it should be odd, the value encoded in it. We do it like this. So L1, for example, L1 is either B0 or the value is odd, right? For L2, is this the same? L2 is either 0 or if the value is not 0, it should be odd. And additionally, there is another rule, which is that if L2 is not 0, then this is the imply operator in POC, then the level 1 should not be 0. So basically, if L0 is used, LB1 should be used. If L3 is used, L2 and L1 should be used, and so on. And this is how we encode it using constant expressions. Okay? Then we have a pretty printer to give it, to pretty print the tag, in a way with name and everything. So this is how we encode the GCOV tags, right? Now, one thing. We could actually show just the bytes corresponding to the tags, but there is a set of tags which are defined for currently defined, and this is how the hierarchy is going to become clear. So let me keep this in this buffer so we see the definition. And here in the pickle, once we have defined the type GCOV tag, we are defining the different tags, which is not that many. Is those ones which are currently defined. And then here, the hierarchy thing should become clear, right? So we have something which is called tag 0, right? A 0 tag for GCOV, which all the bytes are 0. And this is used for special purposes. Then, okay, we have a GCOV tag function, which is a first level tag, in the sense that only L1 is defined with the value of 1. And L2, L3, and 4 and 0. They are 0 because in the constructor here we are not specifying value for them, so they default to 0. Then we have a blocks tag, which is a second level tag. You see, that's why L0 is defined here. And the associated first level tag is a function, so this can be interpreted as the blocks, they belong to a function, to some given function, and it has this L2. The arcs is the same thing, the arcs belong to some given function, the lines the same thing, and then we have the counters tags. Counters, and then for example we have another first level tag, which is the object summary, which it's is another first level tag. And then the program summary, which is obsolete. This is one is not used anymore, but we support this here. Why not? So now I hope that the hierarchy thing is now clarified. Yeah. Okay. So when you look at it in POC, it looks simple. When you look at it in this implementation, it's awful because it's not that easy to understand actually. Okay. Now, this could be enough for us, right? Because now we have the different tag values, and actually, since it is an integral struct, we can actually operate with them. For example, tag args. Okay, it is pretty printed. It is 2 levels, but we can also get the numerical value, operate with it because it's an integral struct. And of course we can access, L2 or L1, right? Fine. However, note something. When we use the pretty printer, it says args. So it is showing us the bytes, but it's also saying args. So where is this args coming from, right? And this is I'm happy that I can show you this because this is something that we use in many pickles and it's becoming a very common idiom. Basically, POC is a domain-specific language, but it is a full-fledged programming language. And this means that, for example, not every type that you define in POC should correspond or must correspond to some stored data or stored format. No. You can use POC code and POC structures as auxiliary things to actually make your pickle more useful. This is one example. So we have a little registry of metadata for non-GCOV tags that are used for pretty-printing and for documentation purposes in this case. So basically we have an array in our pickle, which is called GCOV tag info, that is initialized as an empty array of those things. And this is an array constructor in POC. They are very simple. If you want an array of int32 empty, you do like this. If you want it as the type of 3, you do like this. If you want like 3 with values initialized to those values, you do like this. Right. Okay. Anyway, that's basic POC, not the topic of this video. So so basically each entry in our little registry is associating a tag number. Note that it's not a GCOV tag because we don't need that. Those are just 32-bit integers with a name and some documentation. And so we have the registry here, and then after we define the currently supported tags here, then we fill in the registry, right? So we set it to an array of GCOV tag info for the different ones, specifying useful names, meaningful names, and also some documentation, right? So in the pickle, we have this array, right? That with this little registry. And then we use this registry in the pretty printer of the tag itself. So in the pretty printer, we iterate on the different entries in the register, and then we extract a meaningful name for the tag if we find it, and then we compose, the whole thing. So this is nice because if we ever, as soon as when GCC updates the format and adds a new kind of tag, for example, then we can just add the new variable here, and we can just add the new entry in the registry. So it sounds like elaborated, but it's not. I mean, it's like, like a few lines for defining the struct type and the array, and I think it's quite readable and quite straightforward. And we could provide some language level fixed facility for doing things like this, but this is better because this you can do whatever you want. You can have your own registry. Other big pickles, the big pickles like the elf pickles, they have like more complicated registries, but I like that people can define their own registries, in 8 lines of code. I mean, that's nice. Anyway, let's move on. So those are the tags, right? So in the record. Now there is a record length. So how record lengths are expressed in GCOV? Well, not the straightforward way again. So basically, the length is stored as an 32-bit integer, which is signed, but if the value is negative, it is to be interpreted as 0. So this is weird. I mean, you may wonder, so why this is not stored as an unsigned 32-bit integer? Well, because of this basic encoding thing. I interpret. I mean, I'm speculating now, but I think that whoever designed the first version of this, whoever designed this format said, okay, well, let's have this basic encoding. Everything is assigned in 32-bit integer, or a 64-bit integer, or a string, right? So how do we translate that into POC terms? So in this case, it's not an integral struct, because it's just a struct with one field, which is assigned 32 bits length. And then we have what in POC we know as computed fields. So a computed field is like a normal field. So in this case, it's a field called value of type offset, 32 bits signed offset with unit bytes. So it's an offset in bytes, but it is computed, meaning that it's not mapped. So it's not created, built from some, it doesn't really exist stored in the struct, this value. But instead, we provide two methods named in the proper way. So this is the name of the field, this value. So we have to define a get value and a set value method. And in this case, this computed field is a synthetic field that when you read it using the normal notation, when you read it, it gives you, if the length is less than 0, it gives you as 0 bytes. Otherwise, it gives you the length as the magnitude of an offset with bytes unit, and it does the right thing in the set, plus a pretty printer. So this is convenient because, so we can see here GCOV length. If we build one, is 0 bytes, right? And but if we say length equals 30, it is 30 bytes. And but here, well, okay, that's the pretty printer, right? But if length equals -3, it is 0 bytes. And if we say if we access the computed field, so var L GCOV length, so L is 0 bytes, but L dot underscore length is -3, but L dot get dot value is the computed field, which is 0 bytes. And if we say 23 bytes, it does the right thing. Okay, so this is a computed field for us. So okay, yeah, so this works. Then following the length of each record, in each record, then there is the variable part of each record, right? And the variable part, it depends on what kind of record it is. So we will go through them now, but before that, let's take a look at the records. So in the data file, records, so it's an array of records. We said it's an unbounded array, and now we know what we are looking at. So first we have a first level tag for an object summary, and it's a first level tag, which makes full sense because this is just the first one, right? The length of the variable part of this kind of tags is, of this particular tag, is 8 bytes, right? And in this case, the payload, so the data field, is an object summary struct, which is runs2 and some max 5. So remember that we ran the test program twice, so that's why runs here is 2. Remember also the GCOV summary, it calls GCOV runs 2. So here we are, it's there. And the second record in the data file is a function that we will see now what it is. It's a first level tag. The length of the payload in this case is 12 bytes, and then it has some different payload. And then we have counters here, counters for args, for example. The length, this is a second level tag. So basically the first level tag is this function 1, right? So this is a second level tag corresponding to a function first tag, right? So this is a counter args, an args counter for this function, and so on. Okay, so let's take a look at the different payloads. So okay, so first let's have the function. So the payload for a function, it comes in 2 different flavors. There is a simple one, which it gives you this ident, which is a number that identifies the function. I don't know how this number is calculated. It may be an offset from the text section or something. Then this line number checksum, and a control flow graph checksum, and those are checksums calculated somehow. And this short version is used in the data files. So I think the data records, it was the second one is a function one, right? So the second one is a function one, and this is using, like the small version, you see. But the extended version is like the small version, the first 3 fields, but it has a lot of more things. It has a name, the name of the function, if a flag is artificial or not, the source file where the function is defined, and then line column information. And then we define it like this in a POC type with a nice pretty printer. The extended function versions, they are used in the nodes. Let's see. Oh, look, it's the first one, which is the first function actually. So records the first, and you can see that is the same tag, but the length is different. And so in the data, it's using the small version. In the in the notes is using the record with the big version, with the long version, which is pretty printed. Okay, now how to distinguish both? Because at this point we don't have visibility whether this GCOV record is stored in a notes file or in a data file. So basically what I did here, which I think it's an interesting idiom, is that, okay, so if the tag is a function, if it's a function tag, and the length specified corresponds to the size of one simple GCOV description. Remember, GCOV function is this little type here. Then use it. Otherwise, if the tag is a tag function, but the size is not the size of the smallest tract, then assume it is the biggest tract. So this is how. So this is why, in this case, the tag is the same, because the tag is exactly the same in both files in both records, in both files, but the length is different. So in this case, the length is 12 bytes. That corresponds to one GCOV function. Okay, in bytes, please, is 12 bytes. Okay, so that's the trick. Okay, what else? What other records we have? Okay, we have object summary record, which actually in the data I think is the first one. Yeah, it's an object summary is the first one. So the summary is the thing that contains the runs and the summax, right? So so the summary is here. It doesn't even, I didn't even add a separated GCOV type for it because it is so trivial. I could. I mean, when you write pickles, when to use an internal struct definition like this, or when to use a GCOV object summary type, external type. Well, if you think that the user might find it useful to create new or to map separated object summaries, then do it. Then get it out into a type GCOV object summary, and then people could do it like GCOV object summary constructed or map it or whatever. But if not, you can use an internal definition. If at some point that becomes obvious that it's useful, we can change it. But, okay, what else? What else is around here in the data? Okay, we have counters. So counters are actually the data that we are interested in, right? I mean, in this case, for example, this is the counter for some particular arc, right? For some particular arcs, and look, we have the integers. You remember the 64-bit integers, the weird encoding of them? Well, we are seeing there here. So 2551, right? If we go to the GCOV report, we can see that those counters, those arc counters, are actually those numbers, right? Some of those numbers. Now again, so this is the counter, but this is a counter, right? This is a counter, which is what is a counter? A counter is that is an array of 64-bit integers, GCOV integers, of whatever number of them fit in that length, right? But let's see at the arcs. These arcs, which is not the same as the counters, they occur in node files, and look, they identify a block number and an array of something called GCOV arcs, and this GCOV arcs is basically the connection of two different blocks, right? So this block number is the origin, and basically in the node files you have, okay, let's say, we have nodes, records, not records. Let's look for an arc. Here. So, for example, this one. This one is defining the arcs from the basic block number 0. So the basic block number 0, it has it jumps, or it transitions, right, into the basic block number 2, and then with the flag fall, right? And so basically that is each element of that array is one GCOV arg. So it is a destination block, the flags, then we have a pretty printer, and the pretty printer basically still is printing in a pretty way. Yeah, I mean the flags here. This is a very common way of doing it, actually, right? You start with the arg convention that we use, the destination block, and then you add, you know, whatever commas, you know, into the description. So in this case, for example, here from the basic block number 2, we have to go to transitions, which is to the basic block 5, and well, sorry, we have 1. Well, this isn't, well, yeah, our little program is not that interesting. Oh, look, this one is better. So from the basic block 3, it can transition to either basic block 4, basic block, or basic block 1, right? Which is a fake one. I don't know exactly what that means, but doesn't look good. And either to the basic block 4 or the basic block 1, right? But note, this is the nodes file that complements the data file. So if in the data file we look for the counter for basic block counters, yeah, well, anyway, whatever, those are the details of what is encoded there. I don't actually remember how it works, but so this is the payload for GCOV arg, right? What else for the lines? GCOV lines. Okay, we should wrap up because this is getting too long. But for the lines is something similar. Basically, it's per block, right? Per basic block is what is which lines in the source file corresponds to this block, and you can see here that there is for the block number blah blah whatever, it associates n lines, which could be 0 or more lines, and then it encodes this following certain rules with some terminating. This is an unbounded array, so basically you have to be careful to have the constant expressions to guarantee terminates when it maps and so on, right? Then the blocks, the basic blocks, right? Which I think it tells you that should be the nodes, right? Blocks, yeah, 10. So it has from 0 to 10 basic blocks, or from 0 to 9, I don't know. And then the counters. And then note that's not something here. We know that those are the tags that I managed to identify while reading, which has documented in the header file in GCC, and that I managed to identify while I read the code. But it turns out that you can find weird ones too. And actually, okay, you see we are not seeing all the records there, right? How many are there? We have 25 records in the data file. Okay, so this is because by default the output of setting in POC is 5, meaning that when you print values of arrays, it only prints until the first 5. So let's put it to 50 temporarily, and let's see the records. So yeah, so you see those records here, those records. The 2-level records, 0145, 0145, those are records with tags that I don't know about, and GCC must be using them for something, but I don't have them here. So I could have made this type, the GCOV record, to actually fail in this union. I mean, if I don't have this, this last field here, then it will fail when it finds a tag it doesn't meet, a record it doesn't recognize, because no valid alternative in the union will actually succeed. But I have this last here, which is, if you don't know what this record is about, let's just map an array of the corresponding bytes, you know, of the length. And then finally, well, that's what we are seeing here. And then finally, we have a constraint in each record to make sure that the size of the payload actually corresponds to the length. And that is it. I mean, this is it for the nodes file and for the data file, right? You can use something that I love. I'm so happy about this. You know, this dump val support, which I recently added. So for example, for the data file, this is, you know, the magic is there, then it's the version, then in yellow the stamp, the checksum in brown, then the current working directory, and then the records, right? And then you say, okay, and show me the records, which was number 6, right? Or actually I could say like this. And then the records, you can see here byte dump, you know, with the different colors for the different places, right? Tag, length, date, and so on. And I'm so very happy with this dump val command, because and dump is all written in POC itself, including the colorizing and everything. So if you are curious, take a look to it. Okay, the last thing I wanted to mention here is that there is a third little brother here, which is this file name header, which has this magic number GCFN. So what is this used for? Okay, note that we have here in our example, we have a notes file generated by the compiler and a data file generated by instrumentalization code, or updated by it every time you run the program. And when you run GCOV, you get a report and it knows where the source code of the program is, and from the data file, right, and the notes file. And remember that extended version of the file. You know, that's where it's getting it from. I mean, notes, records. Yeah, here you see this foo.c. This is the source field in this function record entry, and the GCOV utility is using that to actually look for this file, and then get the source code, get the line records, using everything together to give you this nice report. However, sometimes in some settings you don't get this information in files, particularly the data files. Imagine, for example, that you want to profile or to get the coverage of a kernel, for example. Then you may be getting the counters refreshed via a special file, for example, but the special file doesn't have the name of the source files. So then for that purpose, when you stream this information, you can intercalate little file name header things like this, which has their own magic number. They have a version, their own version that works the same as the other ones, and then it has a string which is the file name. But this is all. I mean, it's very simple, and that's how it is used. So, to recap, what we did was we had an each. I had an each because for work purposes I had to do some stuff with GCOV files. So basically I want to use POC to access those files. POC did not include a pickle for GCOV for those particular formats. So what I did was to go to the GCC source code. I read the corresponding C header files. I had to read and understand all the macros there and part of the implementation. Then I wrote down, I started with the basic encoding of the file, which is 32-bit integers, 64-bit integers, and strings. And then I went top down. I mean, I went, okay, what is in a data file, what is in a notes file, and then I started creating, you know, all the different types for the strings, for the lengths, for the tags, for the records, and for everything. And the result is a very small pickle, again, for 136 lines, that is now part of the official of the POC distribution. It is in Git, so next time we release POC, it will include the GCOV pickle. People will be able to use it, to reuse it, to expand it, to make it better. And so, okay, so I hope this was useful, and see you the next time.